Alright, guys, so let's do these questions. Okay, so I have a lot of notes for us because a lot of basic principles in these questions. These are the really interesting, more mathematical ones. So, okay, 31, we have um, basically two reactions trying to make the third one. So we have two AgCl here. So we got the AgCl on the left. So we do 1 over K1 and multiply it by 2. So we multiply the AgCl by 2. So we got a square. And of course, that's not it because we also got to add the second reaction. Stuff is going to cancel out. So 1 over K1 squared times K2 gives us D. Okay. Okay. Solution of allylamine is 3.61% ionized and has a pH of 11.12. Okay, what you're going to do is this. Follow what I say. Okay. So basically, you're going to write allylamine, the formula, plus H2O gives allylammonium, the cation, plus hydroxide, and allylammonium gives allylamine plus H plus. So we have two equations. First is base, second is acid. Now, what we can do here is find, because we have all this information about the base, we can find the pKb of the base and subtract it from 14 to give the pKa. It's a standard relationship. pKa plus pKb equals 14. Okay, so now what we're going to do is, well, use the information that we have. So the pH is 11.12. This is the base, so pOH is going to be 2.88. So 10 to the negative 2.88 is the concentration of each of those things on the right side of the first equation. Now, if we're trying to find Kb, that's going to be right side squared over, right, over bottom remaining. So if it's 0.0361, if it's 3.61% ionized, that means that 0.0361 of our total amount is 10 to the negative 2.88. So we're going to divide, right? So 0.03652 is the total amount that we have. So we do, for the equilibrium constant, we're going to square 10 to the negative 2.88 and divide it by our total amount, 0.0365 minus 10 to the negative 2.88. Or we could have just done that there is 0.93 39 left, but 9639. My fault. All right. Okay. So yeah. All right. So we get 4.9 times 10 to the negative 5 as an equilibrium constant, and we take the negative log of that and subtract from 14. So we get 14 minus 4.3. All right. 33. Right. Okay. I'm gonna let you guys read this and look at the diagram. Okay. So basically, what's going on here is that there's a weak base, a weak acid, and a strong base, so the pH of the equivalent point is going to be above, 7. So we're basically comparing things here. If you look here, 15 milliliters, that's above the half equivalence point because our equivalence point is at 27 milliliters. So this is going to be 13 point, well, about 27, 27.5. So 13.75, it's a bit above. So there's going to be more of that base and the acid. So we know that C and D are wrong. And then, is it A or B? Well, we have to look, right? If it's A, well, how could it be A, right? Well, there's a reason. Because the Na plus is staying fixed. As you can see here, with M1V1 equals M2V2, we have 0.1 molar times 0.015 liters at this half equivalence. At this point, actually, you get 0.0015 mole of sodium total, right? But it doesn't matter, moles, molarity. What remains is that the moles and the molarity of sodium stay constant. Now there's a twist here. There's an equilibrium at anyone in this any point in this buffer region is going to have an equilibrium. So there's two things here, and basically what's going on is that the formation of the base in this buffer region, because we're above half equivalence point, formation of base is more prevalent than formation of acid. So that's why, because backward formation of acid, forward formation of base, so it's going to be that HCO minus actually is higher than it's supposed to be. So it's going to be higher than Na plus. You would think that since they're both basic, they should be the same, but they are not. So it's A. Okay, 34. Okay, we have a lot of big numbers here and a small amount of CO3 relatively. So we have to think about this, right? Initially, you might be like, Kp is 0.10, K sub P, right? So it has to stay 0.10. You're not tricking me, USNCO. I got this right. No, because this is a weird case where D is actually correct and it cannot be determined. So let's analyze this, right? There's two cases in any equilibrium. You have some amount and you get your equilibrium on the right side. Either all of it is gone, and that's not really equilibrium. You were supposed to have had more so that there's more on the left, because you need to have some remaining on the left, reactants, and some on the right. So with such a little amount, right, you have zero idea what's going on. If you have 3.0 grams solid CaCO3 and the equilibrium pressure is 0.10, or the pressure, not necessarily equilibrium, it could be the first case where there's still enough after those 3.0 grams equilibrate, like there's 0.5 grams left, or there is none. In that case, there isn't equilibrium. That's just a reaction forming these products. If we had had more, then there would have been equilibrium. So, if we add 3.0 gram, maybe that will give us more to have left over when the reaction proceeds. So, there will still be some CaCO3 left. So, that's when we really get our true equilibrium constant, which we cannot figure out in any manner. Okay, this is a simple uh, equilibrium equation. Now, how are you going to do this? Well, 0.6 plus x squared over 0.6 minus x squared right here. So here's the deal. On the exam, you're not going to have a graphic calculator. You're going to have a scientific calculator. So how are you going to do this? Unless you have extremely advanced knowledge of the calculator, I don't even know if it can do equation solving, but you check your answers. Let's choose something that's in between a high and a low. So we'll see, right? The C word. Well, be careful. We're finding SO2. So 0.6 minus x is 0.35. So x has to be 0.25. So plug it in. The 0.85 squared over 0.35 squared give us 2.75. No, it's too high. So if 0.35 gives us something too high, certainly the ones before it will give us higher, because lower pressure of SO2 means a higher x. So it has to be D. And if you plug in 0.19, you see that. Now for 36, how are you going to do this? Okay, write this again. This is complex. Two equations you're going to need to write for KSP and KF. CD2 plus 4i minus gives CDI42 minus, that's a complexation, and CDIO32 gives CD2 plus 2IO3 minus. Okay. Add these up, your CD2 pluses will cancel out. You're going to have the precipitate on the left plus 4i minus gives CDI42 minus plus 2IO3 minus. What in the world do we do now? Well, we're trying to find the minimum amount of ion that would need to be added. So we have y. Let's call that y. So we have y on the left. Forget about the precipitate. 0, 0. Now we're dissolving something. So we have 0.1 mole of CD, which is going to go directly to the complex ion because, I mean, look at that. Such a high equilibrium constant, it's going to go directly to that complex ion. So 0.1 mole CD, 0.1 mole CI4. It's minus, right? Okay. So plug that in, 0.2 for I3 minus. So you're going to have 0.1, 0.2, minus 0.4 on the left. So y minus 0.4, you're going to make a substitution and set that to x because you do not want to have a fourth power of a complex expression. So what you're going to do, again, since you added these equations, you're going to multiply the equilibrium constants as is. So you get 0.0255 equals 0.2 squared times 0.1 over x to the 4. You do your division correctly. Make sure to write this down, and you're going to get your fourth root and 0.59. So that is the answer. Is it? No, it's not, because, well, don't forget this, right? So we got to add 0.99. Okay. Very simple. What is the average oxidation state of molybdenum in the phosphomolybdate ion? PMO12O43 Okay. Get to writing your equation. You got only one variable here. 12x minus 80, because O is negative 2. And P is either 5, plus 5, or minus 3. So you do casework, right? Go for each one. If it's plus 5, you get x equals 6, which is there. If it's minus 3, you get 6.666, which is indeed there. So it's A. Simple question, voltaic cell, okay. Well, zinc is being oxidized because its oxidation state is increasing, and silver is being reduced because its oxidation state is decreasing. So remember the rule, right? Oxidation anode vowels, reduction cathode consonants, right? So yeah, others are just wrong. I mean, how is this right? If AD is being formed, same as this, right? It's being It's being deposited as Zn2 plus. C electrons flow through the external circuit from the silver electrode to the zinc electrode. If you think about this, Ag plus is gaining an electron, so it has to go from the Zn to the silver. All right. All right. So simple electrolysis. Let's do this simply and smoothly, right? 4,700 seconds times 0.130. Remember that an ampere is a coulomb per second, so you're going to be multiplying to find the number of coulombs. Very clean. So you're going to get 611 coulombs divided by Faraday's constant, which is given. Indeed, it is given here in your constant sheet. Don't overlook this. H is really helpful. You should know Avogadro's constant. This is cool that Faraday's can be expressed in two different ways. Yeah, that is pretty cool. I did not know that. I've not seen that before. This is probably when you have a more complex. Oh, like your NRT. Yeah, that's what it is. With delta G and RT. Yeah, okay, okay. Cool, cool. So 96,500, the technical amount is actually 96,485, but I believe so. So whatever. Yeah, so you get 0.006 more electrons. Now you have two cases here. Look at these answers. What's going on? A and C you have +1 as AU, and B and D you have +3. So you gotta be smart, right? You have to be smart here. Because if it's AU plus, it's gonna be 1 mole electron per 1 mole AU, and if it's, 1 mole AU per 1 mole electron, and if it's AU3 plus, it's going to be 3 mole electron. So 1 mole AU, 3 mole electron. So for the latter, you're going to divide by 3, and for the former, you're just going to keep it as is. So let's choose the former. There's 0.006 mole of gold. like 0.0021 or something. Yeah, so let's check this, right? What happens? Well, 1 over this value, that is not close. We get 157.93, not there. So 1 over this times 3, because dividing by dividing is multiplying, 474. Yeah, D. All right, final one. Which factors contribute to inefficiencies in silicon-based photovoltaic devices in harvesting the energy of light from the sun? How these work? These are on your solar panels. Light goes and passes through them optimally, the optimal type of light that they want, which is determined by something we'll talk about in a bit. Passes through, excites your electrons, and, well, electricity. It's pretty right? So silicon is really common. It's used in semiconductors, photovoltaic devices. They work like them, right? So there's something called, let me explain this. There's something called a band gap, which is between your valence band, right? And one sec. You're gonna have your conduction band. This is where the photon passes through, and this band gap is, let's say, 1.1 electron volts, right? If it's lower than this, it's gonna pass through, but it won't have enough energy to excite the electrons of silicon. And, well, what's the point in using it? It's not gonna get absorbed. But if it's higher, it will get absorbed. And the thing here, what 2 is talking about, is photons with energies greater than the band gap of silicon are absorbed by the device, and energy is lost as heat. That excess energy that isn't necessary, it's going to be transformed into heat. So 1 is correct, and 2 is correct. So pretty interesting, unique question, but yeah. All right, peace out.